This video is going to show you how you can use the GPIO protocol to output from your Android Things application. We'll discuss the Raspberry Pi Rainbow Hat and its actuators, in this case the LEDs which we'll use to do the classic blink example. Let's get started. GPIO stands for General Purpose Input Output. GPIO works with a single pin on your board and it can have two states, on or off. This means you can monitor a GPIO pin and know when it changes state, or you can change the state of the pin yourself. Monitoring state changes is known as GPIO input, and changing the state is known as GPIO output. Input is reading the pin, and output is writing the pin. This may seem counterintuitive at first, but consider it from the GPIO peripheral's perspective. If we read the GPIO pin, that is input into our application. If we write to the pin, that is output to the peripheral. Our Raspberry Pi is now plugged in and connected via ADB ready for development. We have the Rainbow Hat connected to the top of our Raspberry Pi. This hat has a lot of peripherals, and amongst them, 3 LEDs. A red left LED, a green middle LED, and a blue right LED. We're going to code our app so that one of these LEDs blinks on and off in intervals. Here are the 3 LEDs, and here is the green LED that we want to program. When working with the Rainbow Hat, we can see how each of the peripherals on the hat is connected to our Raspberry Pi by looking at the pinout diagram. To understand how each peripheral works and determine the protocol needed to talk to it, we should consult the Rainbow Hat documentation and, if needed, the specific peripherals datasheet. In the documentation shown here, we can see the 3 LEDs are described as 3 LEDs, red, green, and blue, via GPIO. This is the hint we need to tell us to use GPIO protocol for our communication with the buttons. Now let's double check the pin we need to use by referencing the Rainbow Hat pinout diagram. Looking at this diagram, we can see at the bottom there are the details of the 3 LEDs. Let's choose to use the green middle LED. This has the pin address BCM19. We should remember this for later reference. Okay, let's program the LED. Here, I have an Android Things project already set up in Android Studio. If you aren't sure how to get your project to this point, you can revisit the previous First App lesson for instructions. First, we create an instance of Peripheral Manager Service using this code. This is the Android Things SDK class that allows us to open connections to different board pins using the different available protocols. Using this instance, we want to open a GPIO connection with the pin address we saw earlier on the pinout diagram. When we open this connection, we are given back a GPIO bus variable that will now allow us to communicate using the Android Things SDK GPIO class. We'll use this variable in multiple Android activity lifecycle methods, that's why we make it a field. Notice that we have to wrap the open GPIO call in a try-catch block. This is because the method, and most other methods we will use in the future, all throw a potential IO exception. This is due to the fact that we are dealing with hardware, and at any moment the pin or the peripheral could become unavailable, for instance because of a loose wire. At that point, calling the method would throw this exception. We are assuming that all our wires are nicely connected, and if we do get one of these IO exceptions, it would be really bad for our app, and actually we want to crash straight away so that we can diagnose the problem as soon as it happens. That's why in the catch block we throw an illegal state exception, as we are not expecting nor wanting this to happen. This is known as failing fast and is a clean code best practice. The benefit of this is our bus variable is either a fully instantiated field at this point, or our app has crashed. Therefore, from this point on, there is no need to check if our bus field is null, it never is. Opening a connection to a pin is capturing this pin as your resource. And like with all resource management, it is good practice to release resources once you're finished with them. Also, if we have an open connection to a pin, no other code can open a connection to that same pin until we close our connection. Since we opened the connection to our pin in the onCreate method, we should use the symmetrically matching pair from the Android lifecycle to close the connection. Therefore, we close the GPIO bus connection in onDestroy using this code. Again, close can throw an IO exception. We don't do anything about this if we get an exception, but we can log it out so that we know next time our app starts if something unexpected had happened in the past. Once we have a connection to the GPIO bus, we now have to configure our pin for GPIO output to the LED. We set the direction to out initially high using this code. This means we are telling the GPIO bus that we expect to use this pin as an output, i.e. we expect to send information to the peripheral on this pin. The initially high part of the constant ensures that the initial state is set correctly as we configure the bus. We set the active type to high using this code. If you remember the reference document, the document describes the LED setup. Although you can normally reference the datasheet to find this active type, this is not stated here. Most LEDs are active high, and because it's not documented, we will go with high, which I know because of trial and error is correct. These configuration methods also each throw an illegal state exception, for the same reasons discussed earlier. In this circumstance, we will group them together in one try-catch as a configuration error, and again throw an illegal state exception, because if we can't configure our GPIO pin, then our app is useless. Now that our GPIO pin is configured and ready, we want to be turning the LED on and off at a fixed interval. To achieve this, we need to have a looping bit of code for on-off, etc, etc. In Android, one way to create a repeating code sequence is to use a handler and a runnable. A handler allows you to send and process messages to a selected thread's message queue. We do that using this code. Notice when we create the handler, we specify that the main looper is the thread whose queue we want to use. This means after the initial post and each time the post delayed method is called, our toggle LED runnable is added to the queue of the main thread. This lesson isn't about the intricacies of handlers, but understand that this 3 to 4 lines of code allows our runnable to be executed once every second. With the toggle LED runnable, we can now query and then update the state of our LED. To get the current state of our LED, we can use this code. Because we set the active type to high in the configuration, this means a return value of true is the active type, and this means the LED is on. Now we know if the LED is currently on or off, let's use that to toggle its state. Here is the code for that. I've written it verbosely with an if-else statement because I think it reads better and it makes it more obvious what is happening. Setting the GPIO bus value to true turns the LED on, and setting it to false turns the LED off. Let's run our app and check the rainbow hat to show the blinking LED is working. That's it. You now understand how the Android Things GPIO communication with output peripherals works. You can interface with hardware LEDs and control their state, making them turn on or off. This knowledge also transfers to other GPIO output peripherals such as other types of LEDs or switches.